selection sort without comments, and this is selection sort with enough comments so that you can understand it. Now, talking about the asymptotic complexity of the sorting algorithm, we can see that we have we have a nested loop of two loops. So what's the complexity of this algorithm? Huh? The complexity of this algorithm is you should be able to tell me the complexity within like 10 seconds of looking at this algorithm. Yes, and it's quite easy to see. This loop is going from 1 to n minus 1, so that's a big O of n kind of steps. This is constant. This is going from I to n, and we have already seen the triangular loop which looks like that. So, it looks like this. So when I equals 1, for example, j iterates n minus 1 times, and when I is 2, j iterates n minus 2 times, etc. Like 9, 8, 7, 6, 5, 4, 3, 2, 1. So that's this one, that's big O of n, and this one depends on I, and it gives you this relationship that we have seen before, which is the arithmetic series, the sum of the first n elements of an arithmetic series, which is the number of iterations of a triangular loop. In this case, it's actually not n plus 1, but it's actually n minus 1, because I is not iterating from 1 to n, it's iterating from 1 to n minus 1. But all that is important to us is actually not this real equation, but the fact that it is a quadratic algorithm. It's big O of n squared. Now, why weren't you able to give me this answer within 10 seconds? Okay. So the asymptotic complexity of this algorithm is big O of n squared, and I think in lecture 2 towards the end you find an example of a triangular loop which has asymptotic complexity n squared, and where the loop is actually triangular. So selection sort is big O of n squared. Is it clear why it's big O of n squared? Okay, I hear a lot of talking. What's happening? I mean, I know the TAs are not around, but I think you are mature enough. I mean, you don't need a TA watching you. Another what? There's a noise in another lab? I'm hearing it here? There's a noise in another lab? I'm hearing it here? Right. It's a lab I'm teaching anyway. Okay. So, do we understand how selection sort works? Okay. So now we can understand this sentence that we have said. Selection sort works by repeatedly selecting the smallest element from the unsorted part and adding it to the beginning of the sorted part. Does it make sense now? Okay, so there is a sorted part and there's an unsorted part. So the external loop is going to move from element 1 to element n minus 1. each time it moves to the left of this element is the sorted part of the sequence, to the right of this element is the unsorted part of the sequence. And each time, in each iteration of the external loop, what we are going to do, we are going to find the smallest element from the unsorted part, which is to the right, and we are going to add it to the sorted part, which is at the left. Okay. And I think this is wrong here, to the beginning. That should not be to the beginning. Adding it to the sorted part. Okay, because we are not adding it to the beginning. We are making a swap. Actually, we are adding it to the end of the sorted part. So it shouldn't say to the beginning. So this is how it works. That's the algorithm, and that's the complexity. So in other words, if we have an algorithm, if we have an input sequence which has size million, and we use selection sort, then we will end up having a number of steps which is around a trillion. Sorry, that's quite a lot. So selection sort is not really good for very large sequences because it's a quadratic algorithm. Now, insertion sort. Let's see an example of how insertion sort works. So that's our initial sequence. And what we are going to do is we are going to start from the second element, not the first element. And that's because we need, this is not like, in selection sort, we are going to look at the elements to the right. In insertion sort, we are going to look at the elements to the left. That's why we start from the second element, because there is no point in starting from the first element, because there is nothing to the left of the first element. So we are going to start from the second element because there is something to the left of the second element. So we're starting from this area, from this position, and we are going to mark the second element. Okay, so that's the second element. And what we are going to do, we are going to look at the elements to the left of that element. Okay, so what is to the left of 4? 9. So what we are going to do is we are going to move 4 in its correct position. So what we are going to do is we are going to take 4 to the left and keep taking it to the left until we reach either an element which is smaller than 4, or we reach the beginning of the array. Okay, so insertion sort is smaller than 4, or we reach the beginning of the array. Okay, so insertion sort is going to take an element like 4, and we are going to move it to the left. We are not swapping, we are moving, we are shifting. So we shift it to the left, and we stop shifting when we reach the beginning of the sequence, obviously, or when we reach an element which is smaller than 4. Because if there is an element smaller than 4, there is no point in going past it. We have to stop because it's smaller. Okay, so let's see how this operates to get more insight into this algorithm. So we start by 4, and then we look at the element to the left. That is 9. So we shift 9, and we look again to the left of 9. Well, there is nothing to the left of 9. There is the beginning of the sequence to the left of 9. So we have stopped, and we put number 4 here, and that's the new state. And then we are going to pick 8. We are going to look to the left of 8. And what's to the left of 8? 9. 9 is greater than 8, so we shift it. And then what's to the left of 4? To the left of 9? 4. Okay, so first we look. Okay, we said we pick 8, and then we look to the left. There is 9. 9 is bigger than 8, so we shift it. and then we look to the left again. There is 4. 4 is smaller, so we don't shift it, and we put 8 right here. Okay, so that's the new state, which is equal to that. Now what happens now? We move to 7, so we look to the left of 7. There is 9, we shift it, and then there is 8, we shift it, and then there is 4, we don't shift it because it's smaller than 7, and we put 7 here. So each time we look to the left and try to find the correct position for the element. Okay, so we shift 9, shift 8, and then don't shift 4 and put 7. Now that's the new state. We pick one, and then we look to the left. 9, bigger, shifted. 8, bigger, shifted. 7, bigger, shifted. 4, bigger, shifted. And after 4, it's the beginning of the sequence. So we have reached the beginning of the sequence, so we cannot go any further. So we put 1 right here. And then we continue. We take 6. 9 is bigger shift. 8 is bigger shift. 7 is bigger shift. 4 is smaller than 6, so no more shifting, and we put 6 right here. And we keep doing that until the last element that we are going to shift in the correct place right here, and we get the sorted sequence 1, 2, 3, 4, 5 until 10. So this is how insertion sort works. So we are going to start from the second element, and each time we look to the left of the sequence and we try to put that element in its correct place by shifting all the elements which are larger than this element to the right, and we stop shifting when we encounter a smaller element, or when we reach the beginning of the sequence. Now, can somebody repeat the English description of insertion sort to me? How does insertion sort works? My question is, describe in English how insertion sort works.
The first one is start by second note. The first one is start by second note. Yes, second element, and compare between the first element with the second element from left side. And after that, when the element is second smallest, so change the place to the first index. And continue to all the square in the shape. Say like in the square of 4, index 4, take the number and compare with all the elements inside the index of the left side. With the smallest, replace the element.
Okay, it's almost correct. You just need to be careful that we do not compare with all elements to the left. We compare with the elements to the left and stop when we encounter an element which is smaller than the current element, right?
Yes.
Okay, that's a very that's a difference between selection sort and insertion sort that we will see. In selection sort, we are trying to find the smallest element in the right. So we are always going to explore the whole right, okay, until we find the smallest, and we do the swapping. With insertion sort, we don't have to go to the extreme left, okay. We don't have to always go to the extreme left, because we stop whenever we find a smaller element. This has some effects on the complexity in the average and best case, like we will see. But your description was mostly correct. So we start with the second element and move on to third and fourth, etc. in each time we are going to look at the elements to the left and we compare them with the current element. If they are bigger, we shift them to the right. If they are smaller, then we stop the shifting and we just insert that element in its correct position. The comparison to the element to the left stops when we encounter a smaller element or when we reach the beginning of the sequence. So, which is almost what you said. So that's insertion sort. That's the code for it. So we are going to loop through elements from second to the last. And the current element, we call it value. So A of I is the current element that we are going to compare to the elements to the left. So again, while we have not reached the beginning of the sequence, and while the value that we are comparing to is still bigger than the current value, what we do is we shift to the right. And we continue doing that until either we find a value, we find some aj which is less than or equal to the current value, or if we reach the beginning of the sequence. After we stop the shifting, either because we have reached a value which is smaller or because we have reached the beginning, after that, what we do is to insert the value that we have stored here in its correct position. Now, why do we store why do we store this inside this variable? Why? So my question is explain to me.
Because I want to compare the value with all the elements in the left side.
Exactly, but why do I have to define value? Why did I not say A of I here instead of value? Why did I define a variable value? Because there is some shifting and the value is going to be overwritten, right? Yeah, that's the reason. I'm just checking your understanding. So that's the insertion sort algorithm, and that's how it works. Again, in order to visualize it better, you can go back to the example with all the colors. I tried my best to make it clear. If you still don't get it, that's the same code with enough comments to get you through the sorting algorithm. Again, like usual, what is the asymptotic complexity of insertion sort? This is really the first time we have seen a while loop. For loops are easy to analyze. That's because they tell you, the for loop tells you, I'm looping from 2 to n. So you know that this loop is going to be bigger of n. The while loop does not always tell you that. So this while loop has got a complicated condition. It says while j is greater than 0 and a of j is greater than value. By the way, and then that's not something you find in Java. So all you have to do here is just say and, okay? Just the usual and. This is just some special syntax which tells the compiler to use shortcuts basically in evaluation. It says don't evaluate this unless this is correct. So in Java there's no such a thing like that. So it's and. So the while loop condition is a complicated one, and it doesn't really tell you. You cannot explicitly see that the complexity is big of n, for example. However, by looking at how the algorithm works, your understanding of it, you can guess what is the asymptotic complexity. So again, we said that insertion sort, what we are going to do, we are going to pick this element and we are going to look to the left and shift until we find an element which is smaller, or the beginning of the sequence. So what is the worst case scenario here? How many times are we going to look to the left? Yeah, I mean, if we are here, then the worst case complexity is actually we are going to look at all these 4 elements, depending on the sequence. Can you think of a sequence which is going to force us to always look to all elements to the left? So my question again, can you think of a sequence where we are always going to look at every element to the left of the current element?
Because maybe the element we want to compare with the list elements smaller than it was started like 10, 9, 8, 7.
Yes, correct. Yeah. Basically, elements are sorted in reverse order. So if our objective is to sort elements in ascending order, 1, 2, 3, 4, 5, if the initial sequence is 10, 9, 8, 7, etc., this is going to force us to always check all the elements to the left. If the initial sequence, let's use a smaller sequence like 5, 4, 3, 2, 1, then the insertion sort tells me that I start from 4, I look to the elements to the left, it's 5, so I shift 5, I put 4 here, I shift 5, I put 4 here, and then 3, 2, 1, then I move to 3, I look to the right, 5 and 4. So I shift 5, I shift 4, and I put 3, 2, 1. And then I move to here. And then I look to the left, they are all bigger, so I shift them all, 5, 4, 3, and put 2 here. And then 1, I look to the left, and they are all bigger than 1, so I shift them all, and I end up having 1 here. So the worst case behavior of insertion sort occurs when fill in the blank. The worst case behavior or the worst case complexity of insertion sort occurs when the input is is sorted in reverse order. That's the word which is causing you a problem. Reverse order. Reverse order. Okay, so it's in the opposite order. I'm sure you can invent words. So reverse order and the opposite order, like you said, if we are sorting in increasing order and the input is in decreasing order, then it is going to cause the worst case. If we are sorting in decreasing order and the input is in increasing order, then we are going to see the worst case. So these are all acceptable, equivalent answers of that shows the same thing. So insertion sort again has got so basically back the complexity. We said this is big O of n, and we said this is in the worst case is going to also cause just like selection sort. It's going to cause the internal loop to go from I to 1. Okay, this is like for 1 to I. So in the first time we are going to look at 1 element. In the second iteration of this big loop we are going to look at 2 elements. In the third iteration 3 elements, etc. So we end up having this kind of triangular loop. So in the worst case, this is going to be again a number of steps equal to that, which is big O of n squared, correct? That's in the worst case if we have a reverse sorted sequence. In the average case, when the sequence is is not reverse sorted and is not sorted, we are also going to see this behavior. Now, what about when the input sequence is already sorted?